All right, let's get this going. Okay, so what is it? A little less than 15 minutes. All right, so we're going to get through the rest of these slides here on robustness. What's going on?
Is homework 7 really good?
Let's get to the real issue. I'll talk about it in a second, but the news is good, all right? It's going to be okay. Because I know I have to go through some things. What we'll talk about today is germane to that as well. But certainly you've got the idea of the simulation, which we talked about. So that puts me in the right space, thank you. So instructions. Okay, so this should be, if we refresh, yes, look at that magic. Okay, so I realize now I have these dates in 3 different places, which is non-ideal. So by majority vote, it was the 27th, right? Two of the 3 places said this, so anyway, all right. I just want you to talk to me so I make mistakes. Anyway, so I've made a huge tiny mistake. That's Arrested Development fans, that's what's happening there. It's irrelevant, you don't have to worry about it, but right, so the main thing will be actually, there's a couple of, look at that. There's going to be a couple of analytical pieces. We'll talk a little bit about that today, right now. And then the fun thing is simulating. Mm-hmm. So you can burn some stuff down, but only inside your computer. All right. I know you'll enjoy that. Okay, good. We're done with that thing. Yeah, so a little bit longer for that. Good? That's acceptable, or do you want it this Friday?
Well, is homework 8 going to be a week after that, or going to have 2 assignments due?
No, so I think we'll probably only end up having 8 total, right? So the projects are more of what we're moving to, yeah. I have to give you some stuff on networks. I mean, I'd love to give you assignments
That's okay.
every day. Endless questions. Well, you've done a great job. You've done a great job because we've gotten through a lot of assignments and we've got a lot of material out of the way. I think in some classes past there's been more pleading for mercy. So maybe you just should have said more things. Anyway, so what else am I going to tell you? Okay, so that's good. So we're feeling okay about that. I hope so. Tweets. I'm not sure I was going to show you anything in tweets. Well, the one thing that's been happening recently, I just try to put interesting things here. Of course, is the devastation in Northern California. I mean, and we also have Puerto Rico right now. But we are sort of talking about forest fires. So this is a terrible example. There's an interesting system story, a very important grave one, which is some places people were able to get out well because they'd set up texting services. So everyone was texted. I guess they got everyone to comply and sort of had their names on records. Like someone could just send a text and that would hit everyone, emergency ones, right? So, and that's a hard thing to set up. Not every place had set it up, but the ones that, from what I've read or what I've heard, that where that kind of, this is sort of an immune system response type thing, right? You've got this big, everything's connected, like lots of people together. How do you, what do you impose on top to engender safety? Terrible business. Okay, we'll get rid of that. Oh yeah, so, right, Jeremy had fun. So I'll show you a few little simulations because why not? If they work, yeah, they should work. This is coming, it's on Dropbox. Come on, Dropbox. Is this no, I got them to work at home. Is this some evil UVM thing? Wow, that's amazing. It totally worked this morning. Does UVM have a thing about this? They like Dropbox, right? Or is it, yeah. Apparently we're not allowed to use Slack or anything, or Google or anything, because it's not within, where everything is safe and good. I don't know. I have no idea why it's not working. Wow.
You can imagine it doing things.
What if you download it?
That was it, right? Yes, okay. So 64 by 64 design of 3, which is some level, like it's still going to be a little messy. And is it symmetric both ways, like the distribution coming this way and this way? Yes. Right. So we should see that structure this way. And you can start to...
The design of 3 though, because
it's still messy, yeah?
it's still messy, it only looks at 3 different places. You can see it a lot better.
I'll get the other one. But this, and you've made it go all the way through, right? Oh, well, you can start to see them though. There were these fire breaks emerging, yeah? And eventually it's just got to fill in. It's just going to give up. It's bad. Like, it's a crazy thing to do. Eventually we'll connect them all. So which one should I look at? That one?
Like the 64 by 64 is pretty good.
This one?
Different place.
No, I think it's this, isn't it? That's just super weird. But anyway, it's like reboot the machine level of terribleness. So this is full design. Oh, no. This is D equals 64. So this is checking, like just a linear amount. Right.
You can see it making some, and then when it gets to a point that it has to break them, it'll break them, and then that whole line will disappear really fast.
So it really doesn't want to put trees up here because they all get zapped, right?
And then once it makes a break,
And then it has to give up
they'll disappear really fast.
because none of them are helping. Yeah, that's really good. But that structure there, that very organized structure is really clear, yeah? And it built up, got a lot of trees in there before. Well, what we saw from the paper at least was the yield, right? The maximum yield is almost, right? It's almost when it's full, yeah. Which if you randomly allocate it, no way, right? You only get about halfway before trees burn badly.
Can you refresh our memory what that design parameter is?
Yeah, so it's the number of places you test. Let's run it again because it's fun. So in this case it's 64, but imagine, so let's say 2, so it's going to test, it's going to randomly choose, but there's no guidance to this. We randomly choose 2 locations, and then, for the first one, you put the tree in and then zap everything, run it according to the underlying distribution of lightning strikes, which is more pronounced up here, right? It's decaying this way. See how bad on average, see what the average forest fire size is for that thing, and then take that tree away and then put it in the other place that you chose and then run it all again. And this is 64 in this case, so it's, if this whole thing is L squared, it's 1 over L of that, right? So you're testing, sort of a thin slice, but it's pretty good. It's not bad. And we saw that, at least in the paper, that was not far off testing everything in terms of the kinds of structures it produced. So,
I think there is one in there, the 32 one, where I tested everything. Yeah, for D.
this one.
Yeah. Well,
Yeah, sure, there you go.
see how it now.
This is a Christmas tree farm that you don't want to burn down because you're making money. It's really worried about up here. Is it an exponential decay?
Yeah.
So it's really pronounced, right? Yeah, which,
The L is 3.2, so I always use L of 1 over F, or small L.
so there's a nice break. And like you say, it will disappear. As soon as it gives up on one, it's going to, yeah. Cool. So you can replace the whole Department of Forestry with this simulation. There you go. It's worth it. That's what we like to see. This is the wrong spot. Random forest. We did this. Okay. So thank you. That was great. And I know I had... Okay, so the next things... what was that? John Doyle. Okay, we'll get to him in a little bit. Okay, so how do we feel about the story again? I know I felt like I maybe talked about it so much I confused you and myself. Okay. So here's just a little bit of mathematical stuff we can do for it, just some little optimization things. Oh, I got 2 things. This little guy. All right, so let's see if we can just write down, we'll do a discrete version because that matches up with our simulation, right? We've got a n by n thing that we're working on. see if we can get this to make sense. And so the idea is there's some resource, and that's the effort you put into, for forest, for example. On the next page, we'll have a clear example. It's kind of the effort you put in to maintaining those forest breaks. So if you've got a big area, then sort of per unit area, so there's a big forest break around this big area, which is unlikely to have a lightning strike. That's the story. That's why we're willing to kind of give it up, because the chance that it happens is low. Then at a per site level, right, each site, if you imagine it's sort of sending out resources, imagine these are people or something, because we'll have an analogy to that in a little bit, somehow contributing to these fire breaks being made, then they don't have to do as much, because as area grows, the boundary only grows like 8.5 scaling wise, right? There's more area to sort of support that boundary. So that's a trade-off, and of course you're doing that because there's less likelihood of a lightning strike in there. That's the idea. And so that's why there's this relationship between these two things. Your cost is going down, but if it gets hit, it's going to explode. So this is a very idealized idea that this is how big the forest fire is roughly, and then this is the cost for trying to protect that area. So we want to design it so that we minimize, again, the average size of events, which, again, you can think of a forest fire, and there's some constraint on the XI, right? So that we can't put fire breaks everywhere. We've got some limitation, whatever it is. And then there are all sorts of other considerations, like you don't want to put forest breaks in too much because you start to mess with ecology. Maybe, there are other things as well. And we know that, in fact, when small fires have been prevented, right, you can get into trouble. Yeah, really bad. So we minimize the cost, and that cost is going to be a simple thing. So this is a good abstract thing. We can imagine this is sort of L squared up here, right, if we've got a square beast. I'll try to keep, I think I have this on all the slides, so we can kind of refer to this picture if we need to. And there's some constraint, right? So as we add up the cost associated with each site, then that has to be some constant, some overall constraint there. So this is one of these optimization things, Lagrange multiplier type things, right? We saw that before for the Mandelbrot piece. And so the kinds of, the actual mathematics that you'll end up doing, Lagrange multiplier is a very nice, beautiful thing, but it's just some simple derivatives once you've set things up. So expected size of fire, there's a probability that lightning hits a particular site, and we're thinking of this little square sites. And then there's the area subtended to it. So this is sort of an interesting thing you have to start thinking about. This is true with percolation as well, that you have kind of you can imagine a function, right? So let's say these are our areas, and later we'll be talking about cities, right? So there might actually just be a hospital here and a hospital here and a hospital here populations, right? So there'll be sort of we're going to get to that very quick soon, so I'm excited about that. But these are boundaries around forests, and you can imagine a function, say a of x, and it equals the area of surrounding forest. I'm going to write that badly. Surrounding forest, right? Okay, so what's funny about this function is, right, there's some area here, so as you move around in this space here, this function doesn't change, right? So there's some value for this area, right? This is, say, A1, this is A2. I have to throw this away. Right, and this is A3. So as you kind of wander around on this little curve here and make this A4, so if you imagine traveling along on this little curve here, then you'd have A1, and then A4 would be smaller, say, and A3 is bigger, and A2 is here. So this is traveling on curve. This function here is the area of the point you're at, or the area of the forest that's surrounding you. So it's a piecewise function that's just flat, right? It's an interesting function, and we'll come back to it when we talk about stuff with people. right? But often a lot of percolation theory, you have to think about this too, right? This is some percolating cluster. You pick a site in the cluster. How big is the percolating cluster, or the cluster that's associated with it, right? So you're attaching a global or non-local value to these points. So, right, there's that. Now we have the cost of the firewalls, and this is what I was trying to say before. So this is what this area is, right? This area function. So at site I, it's part of a forest of size a sub I. That typically will have a boundary that scales as a to the half, right? Because it's just a dimensional scaling. These aren't weird allometric. There's no allometric scaling, isometric scaling. And each one of them only has to contribute a little bit, right? So you can divide it up between them. Right, so the idea is this is the cost. It's going to be proportional to the length of the fire break. And then we can divide that cost up between everyone. So we put an a to the minus 1 in here. So now we're going to have a to the minus a half. So this is where our cost is inversely related to our cost of maintaining something is inversely related to the cost of the thing exploding. So two kinds of costs. So it's just isometry. If we go up to higher dimensions, this half gets replaced by, right, these will be volumes, and this would be d over d minus 1 over d. And there's a little question, it's a little bit of work to kind of just go through that and differentiate some things. And you can kind of see roughly what's going to happen. You're differentiating this piece here, this piece here. This is going to give us a negative power, like even further, and you should be able to figure out gamma there. Nice story. So we can do it as well, and I don't have to do this to, you can look at this later on. If we had a continuum story, we're not, right? We don't have to, there's no, for simulations, of course, we're going to do it on a discrete thing, but we don't have to do that for, theoretically. So the same idea, the cost is going to be what's the probability that an event happens at X, and what's the cost of something happening at X. And that's to be, usually that's something to do with the volume surrounding X. So all of this hot theory stuff really generally seems to involve, there's some boundary around a region that prevents things from spreading. So there's a lot of this d over d minus 1 or d plus 1 over d stuff occurring. Right, so something about ewoks. Okay, so, and then we'll have some constraint, right? So there's some resource that the position X is contributing to maintain these boundaries, these borders, and there's some total amount. So for humans, this will be like a tax, right? To look after the hospital or whatever it is. Okay, and again, there's this sort of observation that the volume of, the site is part of that would explode if things went up is inversely proportional to the resources required to maintain that volume's border, right? And so that's a more general thing. And so spatial ones, it's always, there's a dimensional piece here, somehow. Okay, so there's just a few things you can work through it later on. I don't need to show you that, but basically, yeah, that's all right. Okay, where are we now? Okay, so let's connect this. There's been a nice argument. I like to show you arguments between famous people with large brains and egos. This is another one. So this is a very strange thing. So there's a ridiculous Borges reference there, but it's a misreading of the Book of Sand, right? So this is this, let me just point to this object here, right? So this is a sand pile, granular media, very difficult. We talked about it a little bit before, right? It's a complicated thing. Doesn't really flow like fluids, but sometimes it does. Things can get stuck in weird ways. So this turned out to be an interesting little experimental thing. Let's just imagine sand falling down from, right, just out of a little chute. And you can have it come down 1 grain at a time, and it's making a little pile here. And in geomorphology, you talk about the angle of repose, right? At some point, you're going to start to get avalanches. So, okay, let's run this thing, and then look at the avalanche sizes. So this is like a little toy model of things exploding in the real world, natural systems. So the claim was you get power law sized, of course, right? Power law sized distributions of avalanches, right? So lots of little ones and then some bigger ones, and then, it's like the 100-year flood, 1,000-year flood, all those sorts of. So it's sort of comported with these observations of natural disasters. And now and then there'll be a big, piece which will slough off. Okay, so there's a paper, and now it's from, I've got the date on the next one. Yeah, 1987. Okay, so this is now 30 years old. Excuse me, 3 authors, but Per Bak is the famous character behind it all. He passed away, Danish guy, passed away in 2002, he's only 54. Very sad. And so he's sort of famous for, just coming in and saying, I know everything. He was really kind of great in conference. Nice guy in person, but he kind of like sports. In sports, at least in Australia, we talk about white line fever. Someone crosses the white line on the boundary and then they're a different person, right? Lovely person afterwards, you have a beer with them, but they try to kill you when they're playing against you in Australian rules football. So he kind of had that story, at least academically, which was lovely guy, but you get into a conference setting and he's just like ripping shreds off humans everywhere in the great tradition of academics. Okay, so he said, all right, I'm going to make a model of this because, why not? I'm a physicist, I know everything. And this is what it was. So this is a funny little model. So you've got a square grid and you're dropping down these blocks, so we can imagine this Minecraftian thing, right? Here's our grid, and these blocks are falling down. And very simple idea, if you get a stack of 4 or more, if you get a stack of 4, then they go and split apart like this. So sort of a diffusion, kind of, right? So one falls down and they're sort of raining these little blocks. Another one comes down, another one comes down, and it goes like that. Now it doesn't matter what's around it, right? So there could be blocks of 3 here around it, stacks of height 3. So if there's a stack of height 3 here, it pops on top of that one, and then that one goes pop. Right, so the highest anything ever gets is 4 things. It never looks like a sand pile, so it's some sort of weird sand carpet thing, but it has these little cascading things, and it has these parallel size distributions. So this was called self-organized criticality because it seems to just happen. You didn't have to do anything extra, you didn't have to tune it, and it became the great story for where parallel size distributions come from. It is a model that does not in any way resemble the real thing. And then it turns out, I remember being at a conference for granular media in maybe 96 or 7 on Corsica, where there were physicists and engineers just screaming at each other basically about this thing, because apparently this doesn't work. Like if you really study this, it doesn't have heavy-tailed distributions. So this doesn't work, this is really silly. There was another thing, is the idea was that there was a weird pressure distribution under here where the lowest pressure was in the middle, which sort of maybe worked, but no one had ever measured that properly. Anyway, lots of, and the physicists are making models that don't conserve momentum, and it's just really lots of upsetness. Yes, you were going to ask. Oh, that's good too. All right. Okay. Lara, sorry. So that's true. Yeah. So, I mean, we do know that's true from reality, right? But people had never really measured it properly here, because I think sand grains are actually enough to they sort of behave liquidly enough that they fall down. So, we'll get to an example that does the right thing, which is weird. So this is this claim, and people were really taken with this. Good, SOC, right? Self-Organized Criticality. People definitely still talk about this, but it hasn't held up as well, and I'll show you why. It's like having an icing model, which we talked about, the magnetism model that somehow tunes itself to get to the right temperature. And the icing model, will this thing work? I want it to work. Ooh, slobber. I have slobber. So the icing model, if we remember that one, I think I can do it. I can do it. Platypus. Yay. Okay. Sorry. The seamlessness is amazing. Okay, so let's just do it like this. Right, so we had this, sorry. Right, so we had this magnetism, the overall magnetism, temperature this way, and then let's just make it really obvious. Right, so there's some critical temperature, Tc, and as you lower the temperature, and we saw some although actually that visualization didn't work. That's true. Java is dead. You either end up with everything pointing in one direction or the other, right? And so the claim is self-organized criticality is that natural systems somehow just live at this point. There's some self-tuning that drives it back here. And it's only at this point, and you get this out of your percolation model, that you get, so this is a size distribution, right, log 10, because we're good people, log 10, that we get some power law size distribution, right? But if you look at this, you've got little clusters essentially of little tiny magnets kind of lined up with each other, and there are some big ones and big ones and big ones, right? But the largest one is not huge, right? And it's sort of actually, if we think about the 2D version, there's a fractal structure connecting them. If you think about your percolation model, just as you get to the percolation threshold, you get a fractal backbone connecting, and then as you pop above it, you start to get a well-connected piece. So right at this point, there is a largish structure in it, but it's thin, it's fractal-like, so it's tendrily, and it doesn't look, anything like these. So it's basically sitting in here. There's sort of a fractal structure, the largest one, you imagine on big scales, and of course it has nothing compared to these very structured pieces that you see for the hot model, and kind of in reality, right? Okay. So, just this stuff comes for free. We don't need to explain it in other ways. So it's a physical review letters paper. If you don't know, that's the best physics journal in the world. And physical review has A, B, C, D, E. They're not like in terms of how good they are. It's there's X as well now where you pay. Actually, E has always been the interesting one. That's the one where networks and chaos and all sorts of crazy stuff went into E, but it's not because E is a fail. They're just categorizations. Anyway, physical review letters sits on top. So very famous. I think I looked at it before. It has 7,000 citations. It's good. So this is a very specific point for you measure theory fans, right? So it's a of measure 0. Pretty hard to get. If you're away from it, you don't get a power law exactly. Lots and lots of arguing. Okay, so as I said, Purbach, he's one to make bold claims, and he had this book, How Nature Works. You're welcome, fellow humans. I have explained it. And it's the science of self-organized criticality. And you can see, right, he's got the sand dune thing. Lots of beautiful simulations over the years working on that sort of stuff. There are lots of beautiful patterns in snow as well. People have had great fun. Anyway, so it turns out some crazy Norwegians managed to get it to work. As I said, the sandpile thing really doesn't hold up in practice. This is rice between two plexiglass sheets, and so it's being fed in from one end. You've got this block. It's being fed in from one end by a graduate student, right? I'm not sure if it was the same one or another graduate student who is here, like measuring the avalanches. It falls out, and they go and weigh it, and then wonder why their lives are like this. But they get to go skiing because they're Norwegians, so it's not so bad. Okay, so healthcare, oil, right, they're happy. They're very happy. It's true. But oil, suck it, Sweden. Okay, so it is interesting. So money does buy happiness. So let's see. So this worked out. But it's long grain rice. Very important. So this still was a bit controversial, but it does seem to have worked. So under certain ridiculous conditions, and essentially in 2D, this kind of toy model would work. Anyway, strange. Okay, so let's just sort of look at a couple of comparisons. So this is from a PNAS paper, right? So again, one of the top 10 things in the world, Proceedings of the National Academy of Sciences. If you don't know about this journal, right? So I'll just say it's a little funny because it's the old boys, traditionally sort of world of things, because you had to be in the National Academy. So they would publish everyone's stuff in principle, but if you were friends with a member, then that would help a lot, right? They would shepherd it in. That's still a thing. You're allowed to, provide a paper on behalf of your friends. So you see a lot of begging that goes on towards people who are members of this. But it's also got a bit of a bat. So because people would publish their own stuff, they get into the National Academy and they're just like, publish this for me, the thing I just thought of. it's like getting to the Yankees when you're 35 or something, and then just not really producing, right? This happens. So PNAS, so probably not accepted at science or post-nature and science. So there are various, it has a little, but great things in there. More diverse than nature and science too. Okay, so both of these things produce power laws because we're going to compare HOT and SOC. They both have three-lettered acronyms, TLAs. That's important. No. Okay. So one is about optimization, as we've seen. This is this so-called self-tuning, although there's no evidence of self-tuning. It just sort of happens for free, right? So the idea that it really is doing this is a bit of a stretch. There's a special density, right? SOC produces these power law size distributions only at the special density, but only when we have these generic messy structures, right? So this is, the example. And of course we get HOT producing these specialized ones, and that makes us feel better. All right. Okay, so you can go through a bunch of other comparisons like this. We get the robust yet fragile thing out of HOT, right? So it's pretty good, but it can totally explode. Let's see, density and yield. So there's low density for which it's, these systems really work. You can actually get very high density systems that still produce these power law size distributions. The large event shape I mentioned, fractal, right? That's what you get for all of these things at the critical point, all these statistical mechanical systems, percolation, icing model, all these things. But you get you get these compact shapes, right? These are really clear structures. Various other pieces. Anyway, I think that's basically okay. All right. So, all right. The upshot is that HOT seems to work pretty well. It's something you can actually go out and try to play around with. And so this is Mark Newman having some fun. So there's HOT, so let's have cold. And so cold is constrained optimization with limited deviations. Well done. And it's a very simple idea. So we're going to weight the cost of those large ones. So you can just apply a different weighting scheme where you're worried more about this, right? Like this isn't good. So what's actually happening in the pure HOT model is you actually end up with this equipartitioning. This is a really deep thing, I think, right? So that on average, right, lightning strikes are very unlikely out here. They're very likely here. And when they do happen here, of course, big thing happens. And when they happen here, a small thing happens. And so if you multiply those two things together, the risk of the story is basically the same. So this is a big deal. And so this seems to happen over and over again in systems. Fans of machine learning has a lot of that sort of stuff going on too, where you're just trying to equilibrate systems in an interesting way. So I think that's a big deal. And we're going to see that again with the piece that I really want to start talking about. I think we can. Okay, and so all you do is you say, I'm just, as we optimize, as we place our trees, I'm going to be more worried about big events, right? Just sort of maybe scale it in a sort of a way that this is bad, and it's going to push these fire breaks further out, right? And eventually you can make it so essentially, they did some math with this, that you'll have a power law and then a exponential cutoff, right? That's the sort of thing that happens. So you can stop if you really want to build a system like this, you could stop it. Okay, and I think I have this here. Okay, sorry, this should be, boop, okay. So this is actually something that pops out of a lot of systems. This is a very standard kind of form. It's a bit funny to look at to start with, but it's a power law multiplied by an exponential. Now what's happening is, until this x is comparable to xc, right, this is some fixed number, this is basically close to 1, right? So it looks like this until x reaches something on the order of this one, and then after that, this really takes off and goes shoo. And that seems odd, but because you think exponentials, they're dying away all the time, but if this is, 10 bazillion, it takes a while for it to kick in relative to this. Yeah. And there are other beautiful distributions there. We'll talk briefly about that, because not everything is a power law. I don't want you to think that, but there are lots of heavy-tailed distributions. We'll come back to this one later on. Network robustness, this is another incredibly well-cited paper, and I don't really have the pictures. I don't want to show you that. Too much silliness. So error and attack. So this is very influential, but it's basically saying that lots of natural networks are actually really prone to being attacked. And controversial piece, but we'll get back to that when we talk about networks, and that's going to be soon, because it's awesome. Okay. All right, let's start on this. This is great. We good? Hot? Lots of hot. That's enough hot. We took the John Doyle story. You know, you know what? He's like Peter Spector. That's who he's like. He's like Peter Spector. Yeah, right. Just so Lara knows who this guy is. Ego is intact. Okay, so for good reasons. Okay, so so let's think about this. We're going to have this problem where we have, and I've sort of framed this as coming potentially after thinking about distribution systems. So I've yanked this out of the next course, complex networks, because I think it really actually ties together beautifully with HOT, and I wanted to put it in here. But this is, if you look at the name for this is Supply Networks 3, so there are a couple of pieces that come before it, and they're about optimal structures, optimal supply networks where we think about one source and many sinks, like HOT to capillaries, or whatever you want. What's the right way to say that? Right way. Capillaries? Yeah, so capillaries. I had a student who would wince every time I said that. Unbelievable. Anyway, so I guess trigger warning for pronunciation. So we're going to focus on think about things in 2D. We live in basically 2D, right? We kind of move up and down elevators a little bit and so on, but we're sitting on a surface. And we're going to think about, we're going to have many sources for something, or destinations, whatever they are. So it could be post offices, could be hospitals, could be schools. And then the people are all sinks or sources as well, right? Starbucks, you know, we're sinks for coffees or whatever it is. We could have had Blockbuster once. Interesting. Invest in Blockbuster. Okay, so oh dear. So how do we cope with this uneven population density, right? So if everyone sort of lived in this very nice smooth grid, then you just sort of plonk them down at some frequency, right? You'd say, okay, we need that. So if density is uniform, then the sources will be placed out uniformly, right? There's only a few sources relative to many people, say. Think about that. You know, Starbucks, lots of customers, many kids in a school. Actually, that's a little question here, and I've got it here, of course. The hexagonal lattice is the way you do that, because it's awesome. That's something to think about. It's a packing problem. Yes?
When you use the word sources and sinks, can you define it? It seems opposite of how we learned in chaos theory.
Oh, I see what you mean. Well, sources and sinks, and it could be sinks and sources, right? It could be anything, right? So that you so if we think of us as the coffee drinkers or chai latte, then you know, think of us as the sinks, right? And the sources of the Starbucks. And then there's some network structure on top of that has to get the stuff to them. And we'll get to that later. And then there's weirdly cargo ships and stuff, right?
So everything is both.
Yeah.
Coffee shop is both. Okay.
And you know, if you want, you can think of the schools as sinks in the morning, right. And depending on your view of your existence as a parent, then you know that's good or bad, right? So when we used to drop our kids off for, it was still in elementary school at Champlain, the PE teacher would. This is what I mean is when we dropped them off at the end of summer for the first day back, would run around just high-fiving the parents. And the parents would start to kind of like smile and laugh and relax. Anyway, so she understood the system. Yeah.
Does the hexagonal lattice thing go for like materials and stuff?
It does. So anything that's 2D, hexagonal lattice is the best. There are various reasons, we'll come back to it, but graphene, right, is this, no, it's a deep mathematical thing. Anyway, so the graphene is you know, sort of this great example. Recently, an incredibly strong thing. One of the big stories about a hexagonal lattice is that of all the regular lattices, it's the only one in 2D that if you sort of make a big thing of it and squish it in different ways, you can't tell it's hexagonal. You can't tell it's a lattice. It feels like a solid. It doesn't have weird stress and strain patterns. But if you have a square lattice, for example, you can shear it and you can see it. So actually when you run simulations on square lattices, it's always a bit of a bad thing because there's this sort of, the lattice actually matters a little bit there. We should do everything on hexagonal lattices. Chinese checkers. Okay. To go right. Chicken wire. Yes. Okay. I have an incredible crossword clue. Can I give you this? This is wrong. So it's one in a panic throws hook. One in a panic throws hook. You can't get this because it's insane, but also it's Australian. So in Australia you call, so one in a panic is a headless chicken, right? And in Australia you call chickens chooks. They're just chooks. You feed the chooks. Go out and feed the chooks. Put the chooks away. And a headless chicken then is hook. Very good. Oh, okay. All right. Okay, so we're going to look at this work by Stefan, and then Gaster and Newman, and then Umanel, right? So this is a sequence, and you can see this, this is recent stuff in terms of how this has progressed. There's work going back, as with all of this stuff, in the 1950s and earlier. There's work by mathematicians, by geographers, by a sociologist here, and these are physicists, very different people interested in this. Computer scientists have worked on this problem as well. So the p-median problem is what it turns out to be. And this is so we had some fun with hexagonal lattice, but this is our big question. Of course, population density is always uneven, right? So how do we locate things? And so the idea is we're going to have two pieces. We're going to start with this idea that we want to make the average travel time, say, as small as possible, right? So we're thinking about public schools or hospitals. We want to, given how our population's laid out, and that's supposed to be a hospital. So this is the supply most fair. There's also the supply that makes the most money, right? So Starbucks doesn't care about the average distance. I mean, they sort of do, but they really want them to have as many people as possible come in the door. So that's going to be this work by Umanel, which looks at South Korea and the US, and that's the 2009 piece. Okay. Well, there's that too, right? Yeah. I don't know if it's true, but McDonald's apparently made their stuff to be somewhat uncomfortable, the chairs. I don't know if that's true. So that you wouldn't stay forever. Makes sense. Okay, so basic problem. We've got some uneven, so we're going to put a couple of variable names. We're going to have rho for the population density, right? So it's a function of space. And we have n facilities, and we want to put them down. So you can maybe imagine the computational version of this, right? So you're going to start putting them down, maybe shuffling around a little bit, trying to build some sort of optimization algorithm, things you could use that exist. So and this is our game. We want to allocate these n facilities to minimize the average distance between all the people and the nearest facility. So Voronoi cells will matter, which is nice, right? So if you're in between two facilities, the one that's closest, right, is the one you'll go to. So we'll start to draw Voronoi cells around everyone, and that's what this picture is. So this is actually combines data and a simulation. Underlying this is the actual population distribution for the US. This is from this paper by Newman and Gassner. And they just arbitrarily said, well, let's put down 5,000 facilities. So this is an artificial thing on top of the underlying population distribution. And again, it's from what the US looked like in 2000. So they're going to be 5,000 cells. It's for the contiguous US. It's going to be 5,000 cells. And so it should basically start to make sense, right? There are many cells in here that you can't see around the denser places. And of course, they get sparser out here where there's less density of people. And then the question becomes, like, what's the density of these facilities? How does that relate to the density of people? Is it proportional? Right? So as the density goes up of people, does the density of facilities go up in the same way? or does it scale in some way? And that's sort of this great observation that it doesn't grow linearly, it grows as the 2/3 power. So when you see a 2/3 power, obviously you're excited, but what do you think that means? Like, where could that come from?
Area versus volume.
What is it?
Area versus volume.
Yeah, so, and the area, of course, being 2D, right? So it's a d equals 2. So there isn't a volume here because we're just, right? But there is area, and the dimension is 2 dimensions, right? So it's going to be, it looks like it's d over d plus 1. So you're a dangerous physicist person. You're like, I will manufacture something that will do that for you, right? Okay, so here's the fit for it. So you grid this thing and you compute the density of a facility. I mean, one way to do it would be to just say, here's a facility and here's the area. So locally, the density of facilities for this is just 1 over that area, right? You could do that roughly. You could grid it in different ways, but that would be a start. And then you plot that against the population density for that area. You could do that. And we'll see that in the calculations. That's basically how things will work. So population density, this is per square kilometer, right? And so really there's good variation, right? 1 to 5 orders of magnitude. People are not, the way we've organized ourselves is non-trivial. I mean, that's a lot of orders of magnitude. And this is the facility density varying here, and the best line of fit there is 0.66 power. So looks like 2/3. And so we've got the row, and then I'll write it as row facilities and row population. So hopefully that will, because in some of these papers there's a row and a D and whatever. Anyway, so I'll put these subscripts to hopefully make it clear, right? So the density of facilities grows more slowly than the density, and it has a scaling of a 2/3. So why is that, right? That becomes this great problem. 2/3 power. So it's called the size density law in different areas. In sociological texts, it's sort of referred to in that way. I tweeted it, which means nothing, but there's Ed Stefan's work, which we'll follow initially. He has a book online, which I would suggest you look at, and especially look at the final chapter as well, because it's about sociological laws. And so, a lot of sociologists will just sort of frown on this sort of thing, like this is just like trivial or doesn't matter, or I don't know. But geographers tend to be interested in this. I mean, it's a big deal, right? This is how we lay ourselves out. I mean, it matters for all sorts of reasons. And then this is underlying and sort of connecting to the whole, scaling of cities. All that stuff from Betancourt that I talked about back in scaling, about crime and all these other pieces, right? This is another dimension to that. Okay, so this is a different thing. This is referring to some other work that would come in the future. Sources and sinks are distributed throughout the region. Now, that's just for you to kind of have an idea. You can just imagine, here's a source and we've got sinks around it, whatever you want to do, but it's just sort of, yeah. Okay, so the paper we're going to look at, and I know I have to finish, so it was published in Science, right? And so this is a pretty impressive achievement. I think he's at Bellingham, is it the Western Washington University? Is that what's there? Do people know? In sociology. And I've read some of his stuff. Basically, he was not well liked by his colleagues academically, right? They frowned upon his work, and they didn't like it when he got excited about the web in the early 90s. They're like, no, you should. A number of people have these sorts of stories where they started to get excited about what was going on online early on, and it's like, no, you shouldn't look at that. A lot of people dismissed it. Right? Krugman said it wouldn't do any better than the fax machine. Now it's deciding things. Okay, so we're going to look at Stefan's treatment, then we'll look at this Newman and Gaston one, which we'll see actually connects back to work from the 50s, I think it is, or 60s. And here's the idea. How are things broken up? And it's this constraint, right? This idea, it fits in with Zipf's story, actually. So this is actually a kind of an effort. This guy's a big fan of Zipf. Ziv had the principle of least effort, talked about it a lot, didn't actually have any math behind it. But here's a very simple little bit of mathematical stuff we'll go through. As the principle of minimal effort, it's the Homer Simpson principle. We'll go through that, and then we'll get out to a sort of a bigger version of it with Gassner and Newman. Eventually, we're going to look at right? So this is a distribution center for getting the coffee to Starbucks, right? We have to get to that eventually. Like, how do we think about that? We've got all these little local distributing things. How does that work? So that's sort of the end of that. We'll look at maps. It's going to be fun. Okay. All right, people. Escape.